Okay, that was loud. Someone's eardrums are with some earpods that are going to be screaming right now. We're going to be taking a look today at the introduction to separable differential equations. A differential equation in the form of dy over dx is equal to f of y times g of x is called separable. We're going to separate the variables by writing it in the form of 1 over f of y times of d of y is equal to gx dx. This is not going to be what all of your differential equations are really going to look like after you separate the variables. But there is a semester course in college, and it is pretty tough, and it has a lot of applications if you're going into a STEM field of, basically just a whole semester course of separable differential equations. Our textbook has 3 types in it. We only for AP need to worry about one of them, and that is the separable differential equation. You're going to have, some kind of sentence with an equal sign and a dy dx. If you see a y prime, rewrite that as dy over dx. And as you can see by a hint here, this is just a textbook definition. We have a division. Your separation of variables is going to ultimately, you might have a little bit of addition and subtraction to both sides if you have a really kind of funky problem, but basically you're going to be separating your variables through a math operation of multiplication or division or both. Once you get one side of your separable differential equation written in terms of all y's, and the other side has all your references or variables of x, once you have separated the variables, you're going to just simply integrate both sides of this equation with respect to whatever variable has been isolated on that side. So here we're going to be integrating, to get rid of the dy, we're going to be integrating the left-hand side with respect to y, and integrating the right-hand side with respect to x, and then continue, solving the problem, finding both, depending on the information given in the directions, general solutions and particular solutions. Let's take a look at some examples. So our first example, we have y prime is equal to 7x over y. When you're working with derivatives, of course, we do pretty much, even myself will just jump right to the y prime, the sort of shorthand notation for derivatives. The only time we've not used this preferred sort of shorthand for derivative is when we were doing implicit differentiation to make sure that we, applied the chain rule when appropriate. But here and again here it's a little bit unclear about this idea of separating the variables. So we're going to use the expanded form of this notation, which is dy over dx is equal to 7x over y. On the right-hand side, we do have basically like a g of x divided by an f of y. We have x and y as these variables connected through the math operation of actual division. So to undo that division, we're going to multiply both sides by y. And we're in calculus now. We should be able to handle more than one mathematical step at a time. This derivative notation, this is the derivative with respect to x of y, or alternatively dy over dx. This notation has been designed to look and act like multiplication, even though it is a calculus operation. So this isn't truly division, but we are going to separate this variable with undoing the pseudo division, which is to multiply both sides by dx. And we have y dy is equal to 7x dx, and now our variables are separated. And I told you just yesterday when we were being introduced to 6.1 that this is going to be a single point on a free response question if you have one, and the chances are very, very likely you will. If you are asked to do a separable differential equation, you will get a point for separating the variables, even if you have no idea what to do after that. Now we're going to go ahead and integrate both sides, and we're going to be integrating the left-hand side with respect to y and the right-hand side with respect to x. You all are going to make sure that you correct me if I say something silly, right? And what's the integral of y with respect to y? 1/2 y squared. this particular problem, this would be too easy, honestly, for a free response question. If it were, however, you have basically the same equation on both sides. So I would not expect you to get 2 points for this next line of work on a free response question because the functions are so similar. But we do have a coefficient of 7 that I've moved out in front of the integration, and we are just integrating x with respect to x, which of course we all know that that's x squared over 2. And now you introduce the plus c. When you are solving separable differential equations, in general, you need to keep going until you have y isolated, or even gone as far as just solving for y. This time I'm just going to isolate the y squared, not actually taking the square root of both sides. But I do not want to leave that 1/2 coefficient over here. So I'm going to multiply both sides by 2. And thank you. And we get y squared, 7 over 2 times 2. That division of 2 and multiplication of 2 are going to cancel. So we have a 7x squared. 2 times a constant. I'm not going to mark any points off for like a 2 times c, but you would never see that on a multiple choice answer. And honestly, that kind of notation will make your simplification of future problems, more complex problems, well, even more complicated. 2 is a constant. C is an unknown constant. A constant times a constant is simply another constant. And there's not going to be any you don't need to write this as like a c sub 1 and your new constant is a c sub 2. That's not necessary. Just 2 times c is another constant. And we're going to call that done. Is this a particular solution or a general solution? General, because you have the plus c. So on a AP free response question, you would definitely get a point for separating the variables. You'll get 1 to 2 points for integrating both sides. You'll normally have different styles of functions on each side. So that will normally be a 2-point line. And then you'd be getting a point for solving for y, or basically, So let's take a look at something that's certainly a bit more sophisticated. We got another example that says we've got 3y prime plus y prime times x cubed minus 6x squared y is equal to 0. You got x's and y's hanging out. Can we separate these variables so that all the y's are on one side and all the x's are on the other? If you can, then it is a separable differential equation, and you'll just integrate both sides and keep going. So what are we going to do with this negative 6x squared y? Add it to the other side. So we've got 3y prime plus y prime x cubed is equal to 6x squared y. What do these two terms on the left have in common? A y prime. So we're going to factor out that monomial. So we've got y prime times 3 plus x cubed is equal to 6x squared y. Now I have forgotten my parentheses. Now we have done some work so that our derivative is only showing up in one location in our equation. So this might be a good time where we replace the y prime with that dy over dx. How are we going to undo this multiplication? How do we move the 3 plus x cubed over to the right-hand side where there's another factor of x? Yeah, division. How are we bringing the y over? With division. This is a pseudo, it appears to be a division of dx, so that will move over with a pseudo multiplication. And we get a division of y, so we have 1 over y and a dy. We're bringing this dx over with what appears to be an act-like multiplication. We have a 6x squared, and that is over a 3 plus x cubed. Now, once you isolate the variables, and that isolation process is going to involve a multiplication and or division or both. I said and or. Now what do we do with both sides? We want to integrate. So we're going to integrate the left, integrate the right. What's the integral of 1 over y dy, or what's the integral of y prime? Because dy and y prime are kind of interchangeable in what they mean. The integral of y prime over y? Natural log of the absolute value of y. Okay, now just for notes and to be incredibly thorough, and the fact that we're just moving into this realm of the this time in the school year where I'm moving away from every single problem being a full-blown U substitution, especially for what hopefully is going to seem like those easier problems. We have a pretty complex integrand to the right of, on the right-hand side of this equation. Well, what type of function do we have in the denominator? Cubic function. What type of function do we have in the numerator? A quadratic. You know those names, come on. So what is the derivative of a polynomial to a power of 3? Or has a degree of 3? You have a polynomial that has a degree of 2. All right, so pick up on that, Brady. What do we have? If we let u be 3 plus x cubed, what's du? 3x squared dx. If we can write our numerator as a 3x squared dx and not a 6x squared dx, we will have that u prime over u pattern completed. Most of the time we're having to, if we complete the chain rule, multiply the numerator and denominator by a common factor. But, you know, 6 is what? 2 times 3. So let's take that constant coefficient of 2 and move it out in front of the integral symbol. So we have 2 times the indefinite integral of 3x squared over 3 plus x cubed dx. And even if you're not doing a full-blown u substitution, it might be nice for yourself to see it. You do have a u prime over a u. So what is the integral of u prime over u? The natural log of the absolute value of u. Of course, that means it's going to be the natural log of the absolute value of y is equal to the natural log of the absolute value, 2 times the natural log of the absolute value of 3 plus x cubed plus c. Now, when you take a number and cube it, you're not guaranteed that it comes out to be positive. So I don't know what x ultimately is, but x being cubed could be negative, and then plus the 3. There's a good chance with if x is a large, even a small number, a small negative number cubed, this expression could come out to be negative. So the absolute values belong there. Y is a little bit up in the air, but you need to keep going with these problems until you have solved for y. So how do you undo a log base e? What's the inverse math operation? E. Make both sides an exponent of e. So we have make both sides an exponent of e, the exponential function base e and the log base e. Those are inverse math operations. And we've got y is equal to, now let me pause here for a second. I have technically done nothing to remove or justify that these absolute values don't need to go away. Like this is just canceling the log base e. You might have some college professors require you to maintain that absolute value there and then justify later why they go away. I'm seeing it as coming out of the natural log, so the requirement that y is greater than 0 is kind of like being loosened because the y is not in the natural log. I will say on college, when you take these AP tests, you don't need to justify why this absolute value is sort of just disappearing away from the y. It's a little bit of a haziness there in the notation. You can just drop those absolute values, though arguably in a pure mathematics class, you might need to justify why that's going away. You don't need to do that for your AP test. In your exponent of e, you have an addition of 2 terms, which means, you're adding exponents. When do you add exponents? When you're multiplying like bases. So this e to the 2 times natural log of 3 plus x cubed plus c can be written as e to the c times e to the natural log of absolute value of 3 plus x cubed, and then this power of 2 can come up there. A constant raised to a constant is another constant. So you have y is equal to a constant times e. Do we need to keep this e in the natural log? No, those are once again those inverse math operations. That's part of the reason I brought the coefficient of 2 up as a power, is to let these inverse math operations touch. And you have y is equal to c times 3 plus x cubed squared. And you can go ahead and just drop the absolute values and put it instead of parentheses, which arguably anything squared makes that positive. Yay! Okay, so I don't know if that deserves an applause, but maybe a bam. All right, so let me give you this wording. For a third example, the rate of change in y is proportional to the value of y. Solve for y. This wording is going to require you to write your own differential equation and then solve it. It is a very common type of setting for these problems and could very well show up somewhere in your calculus test in May. So how are we going to write a differential equation out of this? The rate of change in y. What do you think that we need to write in response to reading the rate of change in y? Yeah, rate of change is language for slope. And what gives us slope in calculus? There you go. So the rate of change in y, now you're going to have to go through, and I made this up, so I'm leaving a little bit out here. I'm going to do this in terms of time. So we have, or maybe we'll keep it in terms of x. Let's do this as the derivative with respect to x of y is equal to, well, that's equal. Okay, so direct or proportional variation. Anybody remember what that represents or how to write that in from Algebra 2? Proportionally or direct variation. So I'm trying to get you to think back to direct or proportional variation versus indirect or inverse variation. Direct or proportional variation is going to be some kind of variable is equal to k times x, or some constant times a variable. So as your independent variable increases, the y is going to increase by some constant value. So direct or proportional variation from in the Wayback Machine of Algebra 2, and I did actually kind of forget that we had that issue freshman year, for you all it's freshman year. Y is equal to kx. So that's direct or proportional variation. So you want to make a note of that somewhere in your notes. Inverse or indirect variation, which will also show up in your homework, and hopefully if I have time in the notes, is going to be y is equal to the constant, and your independent variable, instead of being a multiple, is going to be a division. So like when we have our problem that says the rate of change in y, the word is your equal sign, and then we've got another portion of this problem that reads proportional to the value of y. So that is bringing in a ky into your problem. Some unknown constant times y. Now, so we have from this setting, from this language, dy over dx is equal to k times a y. Let's separate the variable, solve this, and see what we get. So multiplying both sides by dx and dividing both sides by y, we've got 1 over y dy is equal to k dx. Now, you're not going to get natural log as an answer to, within every problem of separable differential equations, but because you're separating the variables through division, it is a pretty common setting. So one more time, we've separated the variables, and well, only one more time, we're going to do this a lot, but integrate both sides with respect to that isolated variable. What's the integral of 1 over y dy? Yeah, the natural log of the absolute value of y. We have an unknown constant, and the integral of 1 with respect to x is just going to give us x. So we have kx, and then there's your unknown constant, plus c. You need to keep going until you solve for y. So we're going to make both sides an exponent of e to undo the log base e or natural log. And so we have e raised to the natural log of y, absolute value of y, is equal to e raised to the kx plus c, which means we have y is equal to e to the c times e to the kx, and a constant raised to a constant is another constant. And if you remember from, again, algebra or pre-calculus, you have an investment formula that says the amount in an investment is equal to the principal times e to the RT power, your PERT formula, when you're talking about continuous compound interest in, your continuous compound interest in finance. So the rate of change in your investment is going to be proportional to the value of your investment. If you invest $1 and it earns 7% a year, it's going to double in 10 years, so your $1 will become $2. If that $1 is $1 million, though, within 10 years it becomes $2 million. So it's still the same rate of growth, but more is growing. So in absolute terms, your money's making money and your net worth is going up faster at the end of an exponential growth function. Here we go. If you are given a solution to an equation and asked to check the answer, what do you do with it? Plug it in. So this is your equation. You know it. You know that because it has a differential in it. This is the solution to this differential equation. We're just simply going to take this answer, plug it into our equation, and make sure the two sides match. So we've got 2 times y, and then we're also being asked for y prime. And then that's going to be, we're making sure that that's equal to 2 times the sine of 2x minus 1. Or y is the sine of x times the cosine of x minus cosine of x squared. And then to that, we need to add y prime, which means I'm going to have to step off somewhere and probably not even have enough space. But if this is y, let's find y prime. I'll just have to erase this. If y is sine of x cosine of x minus cosine squared, how do we find y prime? What do we have to do to the first term? Or yeah, we can just call these out. What rule? Product rule. So the derivative of the first, the derivative of sine is cosine times the second, plus the first factor, sine, times the derivative of the second, the derivative of cosine is negative sine. And that comes out to be our first derivative, y prime is equal to, read the whole thing. The derivative of cosine squared of x. So what's the derivative? What do we have to do for our second term? Chain rule. So bring the 2 down. So we have minus, better drink some more coffee. So we have minus 2 cosine of x, and then we have to finish that chain rule. So the derivative of cosine is negative sine of x. So we have y prime is equal to, I definitely did not leave myself enough room, cosine squared of x minus sine squared of x. Negative times negative is positive, so plus 2 sine of x cosine of x. I'm putting the sine of x first because of that double angle identity that's coming up. All right, so we got our 2y, 2 times y, plus y prime. If you all watch me, I'm sure this is correct. We have cosine squared of x minus sine squared of x plus 2 sine of x cosine of x. This is looking to be awfully pretty, isn't it? So it starts canceling out pretty quickly? Yeah. Okay, so what's the next step? Distribute. Yeah, get rid of the parentheses. So let's distribute the 2. Nothing to do here because that's just plus parentheses. So we have 2 sine of x cosine of x minus 2 cosine squared of x plus cosine squared of x minus sine squared of x. Is this all good so far?
Yes.
Plus 2 sine x cosine x.
Yeah.
Yeah, this one's
Okay. All right. So we've got 2 sine cosine, 2 sine cosine. So that's going to be 4 sine of x cosine of x. We've got a negative 2 cosine squared plus cosine squared is minus cosine squared x minus sine squared of x. We can do what with these last two terms?
Bring out the -1.
Factor out a -1, so we have 4 times sine of x cosine of x minus cosine squared x plus sine squared x as we factor out that -1, but then sine squared plus cosine squared is going to be equal to 1. And 4 times sine of x times cosine of x. Okay, well, we have a double angle identity. You don't have to remember all those 16 identities you learn in pre-calc, but there's a few that show up fairly often. This is one of them. Obviously, sine squared of x plus cosine squared of x is equal to 1, that first Pythagorean identity. This double angle identity for sine, you could maybe expect to pop up on an AP test. And also, I thought this might show up with the cosines and sines showing up with a difference of right here, cosine squared minus sine squared. I thought this was going to end up being a use of a double angle identity as well, but turns out it was not. But cosine of 2x is cosine squared x minus sine squared x. As it turns out, we didn't need that. If we pull the 4, write that as 2 times 2. We have 2 times 2 sine of x cosine of x, and then minus, of course, this is 1. And 2 sine cosine is equal to the sine of 2x, which is what is on the right-hand side, as long as you follow through with all of your calculus. Thank you, ladies, and everyone else that was yelling at me. That is the right-hand side, so that does check out. That was number 11 in your homework, I believe. Okay. Number 2 is also a homework problem. It was also the last example in our video, in our class notes. So how are we going to, what are we going to write out of this first sentence? The change in y, the rate of change in y is proportional to n. Just yell it out. Rate of change is slope. Slope in calculus comes from derivatives. So anything that talks about rate of change in calculus is going to give you a derivative. So the rate of change in n is the derivative with respect to whatever the other variable is in the problem, and that's t. So the derivative with respect to t of n. So dn dt is equal to direct or proportional variation from algebra 2 and pre-calc was y equals k times x, and inverse or indirect was y is equal to k divided by x. So the rate of change in n is proportional, is equals proportional k times a constant. That constant is multiplied to n. And this sentence is pretty common in AP style questions involving the beginning of the introduction to solving separable differential equations. So you may want to memorize that, and this actually has an answer, which we talked about last week, ends up coming out to be basically the PERT formula. But to make sure that you are grasping the idea of separable differential equations, we're going to solve this, even though I'm hoping that for this particular differential equation, you start memorizing these answers. This particular answer, excuse me. We're going to bring the n over with division and get 1 over n. dn is equal to some kind of constant. And we're going to move this dt over with something like a pseudo multiplication. And once we separate these variables, you're going to integrate both sides. The integral of 1 over n dn, natural log. So we have the natural log of the absolute value of n. Now on the other side you have a constant coefficient, which is why that can be moved out in front of the integral, and the derivative of 1 with respect to t is just going to give you t. So we have kt plus c. You're not generally done until you solve for, whatever your dependent variable is, and here it's n. So what are we doing to both sides of this differential equation? Making both sides an exponent of e. So we have the log base e and the exponential function base e canceling out. And that yields us an n is equal to, now on the other side we have e raised to an exponent that is a sum of two exponents. When do you add exponents? When you're multiplying like bases. Good. I hope I'm grading some really good quizzes this afternoon. We have e to the c times e to the kt. A constant to a constant is another constant. So you get n is equal to c times e to the kt power. So that's number 2. Oh, that's right. All right, so
T equals 0.
when t is equal to 0, what is the problem? All right. So when t is equal to 0, n is 250. So on a separable differential equation, by the way, your first point comes where? Separating the variables. So this is 1 point. Where do you get your additional 2 points? Integrating both sides of the equation. So, and these are different functions on each side, so I would expect that that would be a 2-point step. Your next step, or next point, is coming up. Thankfully, when you read the question, unlike I'm doing a bad job of today. Arguably, that really should be right here at this step, to be honest. Usually you want to find c initially or immediately after you integrate both sides. But there wasn't much to it, so we did solve for n. Finishing solving your problem for your variable of interest is going to be another point. And your last point, your 5th point, usually it's going to come before this answer, though, is finding that c. Taking your information and finding all the constants. In this case, this goes beyond just solving a differential. It asked you a few questions. It said when t is equal to 0, then n was 250. I got the problem back up. Thank you. So we're going to plug that information in. So n is 250. That's n. We got some unknown constant. We have e being raised to something times t. Thankfully, this initial value is when t is equal to 0, so you don't end up having to do a system of equations, which was going to be my last example, but you all basically, some of you told me you didn't need to see that. So we have 250 is equal to c, so our equation now is n is equal to 250 times e to the kt power. The next piece of information that we got said that when t is equal to 1, n is equal to 400. So you're just going to repeat that process again of taking the given information and plugging it into what is currently your equation. So we know what c is now because the initial condition had a t value of 0. So n is 400. That's equal to 250 times e to the kt power. So when k is equal to, or when t is equal to 1. So how do we solve this for k? Yep, we're going to divide by 250. Nice. So we get 400 over 250 is equal to k to the e to the k power. This reduces to 8/5. So we have 8/5 is equal to e to the k power. And one of the main reasons in Algebra 2 that we learned how to solve or work with logarithms is to solve equations where the variable is in the exponent. This is exponential function base e. So we're going to cancel that math operation with natural log or log base e. So we have the natural log of 8/5 is equal to the natural log of e to the k power. Log base e applied to exponential function base e, those cancel out, which hopefully I'm just writing for notes at this point because we've been working with logarithms now for 2 years. And k is equal to the natural log of 8/5. Now, your final equation is n. N is equal to 250 times e to the k, which is the natural log of 8/5 times t. I'm not going to take the last step of plugging in t equals equal to 4, but we can clean this up some more. I'm writing the natural log of 8/5 times t because, well, when we wrote the solution to this differential equation, the separable differential equation, I said k times t. But, of course, multiplication is commutative. So this t is really either this constant is a coefficient of t or t is a coefficient of natural log. What would be the benefit of that?
Bringing it up or bringing it up.
Bringing it up. You can use the power rule to take the t and bring it up as a power, and the exponential function base c and the natural log are just going to what? Cancel out. Make sure you take these notes down. These are really common test questions. So then n is equal to 250, not just for my test, but for AP. That's why I'm giving these to you in your homework. Those cancel out, and you have 850 times 8/5 to the t power. So when we have dy over dx is equal to the square root of x over 4y, for our third problem, why did I write y prime as dy over dx? Just say it. Separate the, well, it's already a differential equation, but it makes it just a little bit clearer of like the fact or how we're going to separate those variables. How do we get this dx over with this x? Pseudo multiply, even though it's not really truly division, it's a calculus notation. And how do we undo the division of y? Multiply. So you have,
You forgot the negative.
oh, negative, thank you. I'm batting 1,000. All right, so we've got y dy, and you decide where you want to deal with the 4. I think I'm going to leave it over here. So we have y dy is equal to negative 1/4 x to the 1/2 power, right? So radicals are not friendly to work with, so we have the square root of x written as x to the 1/2. We have a negative 1/4 dx. That's a point. We're going to integrate both sides. What's the integral of y with respect to y? 1/2 y squared. We've got a negative 1/4 x to the not 1/2 but 3/2. And dividing by 3/2 is the same as multiplying by 2/3 plus c. So we have 1/2 y squared is equal to, those are going to cancel out, so 2 times 3, we got negative 1/6 x to the 3/2 plus c. Going to multiply both sides by 2 and get y squared is equal to negative 1/3 x to the 3/2. And a constant times a constant is just another constant. And I'm going to go ahead and be happy with getting the y squared isolated and call that a day. So for our last question here, number 4, we've got xy plus dy over dx is equal to 100x. How are we separating the variables? Yeah. So every once in a while, your separation of variables will involve a little bit of addition and subtraction, but that last step of really truly separating the variables is always going to be some kind of multiplication and division. So, but in this case, we want to get the dy over dx by itself first. So we're going to go ahead and, well, and the main reason is we have an x over here to the left and we have an x on the right-hand side. So we got dy over dx is equal to 100x minus xy. The choral answers are getting a little bit quieter now, unfortunately. Factor out a common factor of x. So now we've got dy over dx is equal to x times 100 minus y. Now comes that multiplication and division step of separating these variables. We're going to bring the dx over and the y factor over, and we have 1 over 100 minus y dy is equal to x dx. That's going to be 1 point. You're going to integrate both sides, giving you probably 2 additional points. What is the most common integration rule that we use that has a fraction in it? Yeah, the one that involves natural log, where we have the integral of u prime over u. So let's see if that works out. If our u is 100 minus y, what's u prime? Negative 1. So if we just make a u prime in the numerator by multiplying the numerator by negative 1, we need to balance that outside with a, I know this is basically the same thing as multiplying, but we're going to, just so I can say the same thing every time we do this, divide by negative 1. So if we introduce a factor of negative 1 in the numerator, we balance that with a multiple of negative 1 in the denominator, but that's always going to be out in front of the integration symbol. Of course, I know 1 divided by negative 1 is the same as multiplying by negative 1. I just can't read all my questions. Or finish the problem sometimes. So we have negative. What's the integral of u prime over u? Natural log of u. So it's a negative from out front. Negative natural log of the absolute value of 100 minus y is equal to power up, and then divide, and then plus c. And I think this was another one that was a general solution, yeah. So at this point, we're going to be making both sides an exponent of e to cancel out the natural log. The negative 1 can either come up as the power or be moved to the other side by dividing both sides by negative 1, which I think is generally the easier thing to do. So we're going to divide both sides by negative 1 and have the natural log of the absolute value of 100 minus y is equal to, okay, all this is going to be negative now, so negative x squared over 2 plus c. Now, I just said everything was going to be negative, but I don't know what c is. It doesn't matter if I write plus c or minus c. If I just write minus c, it kind of complicates the rest of the work. So a negative 1 times a constant is just another constant. Now what again? We do this a lot with separable differential equations. Make both sides an exponent of e to cancel out the natural log. We get 100 minus y is equal to e to the, oh look, what are we doing again? Adding exponents. When do you add exponents? When you multiply like bases. So we have an e to the c times e to the negative x squared over 2. And a constant to a constant is, once again, another constant. So we have 100 minus y is equal to a constant times e to the negative x squared over 2. I'm going to add by y and subtract by the this term over here, and we have 100 minus c times e to the negative x squared over 2 is equal to y.